Hello, everyone. Well, I'm going to go over a piece that I recently posted called The Ruliology of Lambdas. So it's a slightly technical piece, but I hope people will find it interesting. What are lambdas? It's a story of pure abstract computation. In fact, historically, one of the very first. But even though it's something I, for one, have used in practice for nearly half a century, it's not something that in all my years of exploring simple computational systems and Ruliology I've ever specifically studied. And yes, it involves some fiddly technical details, but it'll turn out that lambdas, like so many systems I've explored, have a rich Ruliology made particularly significant by their connection to practical computing. In Wolfram language, it's the function function. Back when Alonzo Church first discussed it in the 1930s, he called it lambda. The idea is to have something that serves as a pure function, which can be applied to an argument to give a value. For example, in Wolfram language, we might have something like the following. So we might have something like this. So on its own, it's just a symbolic expression that evaluates to itself, function of x, comma 1 plus x. But if we apply this to an argument, then it substitutes that argument into its body and then evaluates that body. So that's looks like this. So we fed the 8 into this function object. The x was bound to 8. Then 1 plus x was computed, and the result is 9. So the so we in Wolfram language, we can also have something like this. X mapped to 1 plus x applied to 8 gives 9. Or if we set lambda equal to our function, we can just write lambda of x, 1 plus x, applied to 8 gives 9, which is actually very close to Church's original notation that just has lambda of x dot 1 plus x for this. Okay, but what if we want to go even purer and effectively just use lambda for everything without any predefined functions like plus? Well, to set up lambdas at all, we have to have a notion of function application, as in f of x means apply f to x. So, for example, here's a lambda, a pure function, that just has a structure defined by function application, lambda of x and then x of x, all applied to x, and so on, and that whole thing applied to a. So can we do familiar operations like this? Well, let's imagine we have a symbol z that represents 0 and another symbol s that represents the operation of computing a successor. Then here's a representation of the integers 0 through 5, starting with z, then s of z, then s of z, and so on. We're counting the successors to know how many times we add 1 to the thing z that represents the 0. Okay, but let's say we look at s of z. We can kind of factor out the s of z in the expression and write it in sort of a purely structural form like this with in terms of lambdas. So this is now a purely structural part in terms of lambdas. In a sense, we've taken that structural part with a couple of lambdas applied to s and z, but actually we don't really need the s and z here. We can perfectly well just set up a representation for integers just in terms of lambdas, say like this, where we just have lambda of a, comma b, lambda of b, comma b, and so on. These are often known as church numerals after Alonzo Church, not the Christian church establishment or anything. So this is all very pure and abstract. At least at first, it seems very clean. But pretty soon one runs into a serious problem. If we were to write lambda of x, comma x of x, what would it mean? in the x of x, there are x's associated with the x and the x's associated with the x in the inner lambda or the outer lambda. Well, typing an expression like that into the Wolfram language, the x's turn red to indicate that, that there's a problem. And at this level, the only way to resolve the problem is to use different names for the two x's. So, for example, to write it as lambda of x, lambda of y. But ultimately, the particular names one uses don't matter. For example, we could swap x and y, and we'd have something which represents exactly the same object. It's the same function as before. So how can one deal with this? Well, one approach that was actually invented more than a decade before lambdas, and that I actually wrote a whole book about a few years ago, is to use so-called combinators, constructs S and K that in effect abstractly define how to rearrange symbolic expressions without having to name anything, or for that matter, introduce variables at all. So, for example, this form that we have here with lambda of y, lambda of x, etc., can be written in terms of combinators like this. And one can confirm it's just a bunch of s's and k's applied to each other. And one can confirm this by applying, by using the definitions of the transformation rules for s and k and seeing that that actually does give the result x of y as we'd expect. So at some level, this is very elegant, but it's also extremely difficult to read. And is there a way to preserve at least some of the comparative readability of lambdas without having to explicitly introduce variables with names and so on? Well, it turns out that there is, and it starts from the observation that a named variable, say x, is basically just a way of referring back to the particular lambda, say lambda of x, that introduced that variable. And and the idea is that rather than making that reference use a named variable, we should make it instead by saying structurally where the lambda is relative to whatever it's referring to. So, for example, given this expression with lambdas, we can write this in what's called De Bruijn index form like this, lambda of 1 of 2, where the 1 says that the variable in that position is associated with the lambda that's 1 lambda back in the expression, while the 2 says that the variable in that position is 2 lambdas back in the expression. So, for example, our version of the integers as lambdas can now be written like, I'm just going to show, sorry, I'm showing you here how this lambda, so this is saying lambda of 1 of 2, and we're seeing here that lambda that represents a 2 is sort of 2 lambdas back. It's referring back to that original lambda, whereas the other lambda here, so that lambda there is referring back 2 lambdas back. That x is referring 2 lambdas back to this here, whereas the y here is referring only 1 lambda back to this one here. And so that's why we see lambda of 1 of 2. Well, so with this setup, the version of the integers as lambdas can now be written like this: lambda of 1, lambda of 2 of 1, lambda of 2 of 2 of 1, lambda of 2 of 2 of 1 represents the integer 2, and so on. Okay, so lambdas can represent things like integers, but can one compute with lambdas? Or put another way, what can pure lambdas do? Fundamentally, there's just one operation, usually called beta reduction, that takes whatever argument a lambda is given and explicitly injects it into the body of the lambda, in effect implementing the structural part of applying a function to its argument. So here's a very simple example of beta reduction. And this is which is equivalent to the standard Wolfram language evaluation function of x of x applied to a of b of c, and that a of b of c gets pulled in place of the x, and the result is a of b of c of a of b of c. So in terms of De Bruijn indices, this whole setup becomes lambda of 1 applied to a of b of c, then gives that result. And again, we can evaluate that and we get this result here. So this seems like a very simple operation, but as we'll see, when applied repeatedly, this operation of beta reduction can lead to all sorts of complex behavior and interesting structure. And the key to this turns out to be the possibility of lambdas appearing as arguments of other lambdas, and through beta reduction, through beta reduction, being injected into their bodies. But as soon as one injects one lambda into another, there are tricky issues that arise. If one writes everything explicitly with variables, there's usually variable renaming that has to be done. So, for example, this object here, lambda of A, lambda of B, if we inject another lambda of A, lambda of B into that, we have to do variable renaming and create a variable C to represent what's going on. So in terms of De Broglie indices, there's instead renumbering to be done, so that this De Broglie index expression, lambda of 1 of 2, applied to lambda of 2, evaluates to lambda of 1, lambda of 2, where those, again, we had to renumber the De Broglie indices. So it's easy to describe informally what beta reduction is doing. In Wolfram language terms, it's basically just the transformation, lambda of x, comma body, applied to an argument, is body with the replacement slash dot x goes to argument. In other words, given lambda of x and body of y, beta reduction is replacing every instance of x in the body with y and returning the result. But it's not quite as simple as that. For example, if y contains a lambda, as in the example we just saw, then we may have to do a certain amount of renaming of variables, usually called alpha conversion. And yes, there can potentially be a cascade of renamings. And you might think that might have to come up with an arbitrary number of distinct new names to use in these renamings. And once you've done the substitution, the beta reduction of, let's say, lambda of x, comma body applied to y, this can expose another lambda in which you have to do more substitution, and so on. Well, it might sound like a detail, but actually it's quite fundamental, and it's what lets lambdas represent computations that keep running and that give rise to the rich Ruliology that we're going to talk about here. Is it something easier to do beta reduction? Is it somehow easier to do beta reduction with De Broglie indices? No, not really. You don't have to invent new names for variables, but instead you have to do rather fiddly recursive realignment of indices whenever you're in effect inserting or deleting lambdas. There's another issue as well. As we'll talk about in more detail later, there are often multiple beta reductions that can be done on a given lambda. And if we trace all of the possibilities, we get a whole multiway graph of possible paths of lambda evaluation. But a fundamental fact about lambdas, known as confluence or the Church-Rossa property, is that, and related to causal invariance, is that if a sequence of beta reductions for a given lambda eventually reaches a fixed point, which as we'll see, it doesn't always, that fixed point will be unique. In other words, evaluating the lambdas will always give a definite result or normal form. So what should one call the things one does when one's working with lambdas? In Wolfram language, we talk of the process of, say, turning function of x, comma x of x applied to a, or lambda of x, x of x applied to a into a of a as evaluation. But sometimes it's instead called, for example, reduction or conversion or substitution or rewriting. In Wolfram language, we might also call lambda of a lambda expression, but it's also sometimes called a lambda term. What about what's inside it? In lambda of x, comma body, the x is usually called a bound variable. If there's a variable, say y, that appears in body and hasn't been bound or scoped by a lambda, it's called a free variable. The lambda expressions that we'll be discussing here normally have no free variables, and such lambda expressions are often called closed lambda terms. So putting a lambda around something, as in lambda of x comma thing, is usually called a lambda abstraction, or just abstraction, and the lambda itself is sometimes called the abstractor. Within the body of a lambda, applying x to y to form x of y is, not surprisingly, usually called an application. As we'll discuss later, it can be represented as x at y or x dot y. Well, what about operations on lambdas? Historically, three are identified: alpha reduction or alpha conversion, beta reduction or beta conversion, and eta reduction or eta conversion. Beta reduction, which we talked about before, is really the core evaluation style operation. For example, replacing lambda of x, comma f of x, the whole lambda applied to y with f of y. So alpha and eta reduction are, in a sense, symbolic housekeeping operations. Alpha reduction is the renaming of variables, while eta reduction is the reduction of lambda of x, comma f of x to f alone. In principle, one could also imagine other reductions, say transformations directly for lambda of blank of blank of blank, although these aren't traditional for lambdas. The actual part of a lambda on which a reduction is done is often called a redex. The rest of the lambda is then called the context, or an expression with a hole. In what we'll be doing here, we'll mostly be concerned with the fundamentally computational process of progressively evaluating, reducing, converting lambdas. But a lot of the formal work done in the past on lambdas has concentrated on the somewhat different problem of the calculus of lambda conversion, or just lambda calculus, which concentrates particularly on identifying equivalences between lambdas, or in other words, determining when one lambda expression can be converted into another or has the same normal form as another. By the way, it's worth saying, as I did before, that there's a close relationship between lambdas and the combinators about which I wrote extensively a few years ago. And indeed, many of the phenomena that I discussed for combinators will show up with various modifications in what I'll talk about here with lambdas. In general, combinators tend to be a bit easier to work with than lambdas at a formal and computational level, but lambdas have the distinct advantage that, at least at the level of individual beta reductions, it's much easier to interpret what they do. The S combinator works in a kind of brain-twisting way, but a beta reduction is effectively just applying a function to an argument. Of course, when one ends up actually doing lots of beta reductions, the results can be very complicated, which is what we'll be talking about here. Basic computation with lambdas. How can one do familiar computations just using lambdas? First, we'll need a way to represent things purely in terms of lambdas. So, for example, as we talked about before, we can represent integers using successive nesting. But now we can also define an explicit successor function purely in terms of lambdas. There are many possible ways to do this. One example is this here. S is lambda of lambda of lambda in terms of De Broglie indices of 2 of 3 of 2 of 1, which is equivalent to this lambda of explicit with explicit variables A, B, and C. So defining 0 as lambda of 1, or lambda of A, comma, lambda of B of B, we can now form a representation, let's say, of the number 3. Here it is, S of Z, which is otherwise lambda of 2 of 3 of 2 of 1 of lambda, etc., etc., etc. But evaluating this lambda expression, which we just constructed from our lambda expression for successor by applying successor of successor of successor of 0, we can, applying beta reduction to the thing we got here, it reduces to lambda of 2 of 2 of 2 of 1, which is exactly the representation we had above of the number 3. So along the same lines, we can define plus as lambda, 4 lambdas, and then some expression, and times with actually only three lambdas, where these functions take their arguments in so-called curried form. So if we want to multiply 3 by 2, we say times of 3 of 2, and so on. So, for example, then 3 times 2 becomes times of S of Z of S of Z. That's times of 3 times 2, and it's in raw form. It's that complicated lambda expression there. But now we can evaluate this with beta reduction. We can apply beta reduction to this thing, and then after 37 steps of beta reduction, there we have it. We have lambda of 2 of 2 of 2 of 2 of 2 of 2 of 1. In other words, the representation, the church numeral representation for 6. So applying this lambda to unevaluated expressions S and Z, we would get this thing applied to S of Z. We would actually get explicitly the six successor functions applied to 0, which again is our representation for the number 6. Well, we can go further. So for example, here's a representation, probably not the minimal one, for the factorial function in terms of pure lambdas. And with this definition, it's a big mess of lambdas and so on, and de Bruijn indices. With this definition, for example, 4 factorial, which is a fac of successor, successor, successor of 0, eventually evaluates to 24. Later on, we'll talk about the process of doing an evaluation like this, and we'll see that, yes, it's complicated in the default way we carry out such evaluations. I mean, this particular one takes 5,067 steps for successive factorials. The number of steps required is 41, 173, 864, 5067, 34,470, and so on. Okay, let's talk about how to write lambdas. So from what we've seen so far, one obvious observation about lambdas is that except in rather trivial cases, they're pretty hard to read. But do they need to be? Well, there are lots of ways to write and render them. But what we'll find out is that while different ones have different features and advantages of which we'll later make use, none of them really crack the code of making lambdas universally easy for us to read. So let's consider the following lambda written out in our standard textual way. It's a whole combination of lambdas and variables and so on. So here's a representation of how the variables that appear in that lambda expression are related. And yes, since each lambda scopes its bound variable, we could as well reuse y in place of x here. So this is a version of that expression in which the thing that was a y here is replaced with another instance of x. I'm sorry, in place of z. We didn't have to use a z here. We could just use another y in place of, for that second lambda, for that last lambda, for that lambda there, we can use a y in place of the z because that y, that whole thing has been scoped so that it is so that the variables are independent. So, well, one obvious thing that makes an expression like this hard to read is that all the brackets it contains. So how can we get rid of brackets? Well, in the Wolfram language, we can always write f at sign x in place of f of x. And, well, so that's the version of this expression. That's that expression there, written out with explicit function invocations. That's the same expression written out with at signs for those function invocations. And because the at operator in the Wolfram language associates to the right, we can write f at g at x as a way to represent f of g of x. So, okay. Using at sign lets us get rid of quite a few brackets, but instead it introduces parentheses. So what can we do about these? One thing we might try is to use an application operator. In Wolfram language, that's a centered dot that stands for the function application instead of an at sign, where that dot is defined to associate to the left, so that f dot g dot x is f of g all applied to x, instead of f of g of x. So in terms of that application operator, our lambda here becomes this. So that's it with at signs, that's it with explicit function invitations, at signs, and dots. So the parentheses moved around, but they didn't go away. So we can make these expressions look a bit simpler by using spaces instead of explicit at signs or dots. And here we have it. But to know what the representation, what the expressions mean, we have to decide whether spaces mean at or dot. In Wolfram language, at tends to be much more useful than dot, because, for example, f at g at x conveniently represents applying one function, g in this case, then another. But in the early history of mathematical logic, spaces were effectively used to represent dot. or application. Oh, and lambda of x, comma body was written as lambda x dot body, giving this is now this expression that I have on the screen is now the sort of traditional mathematical logic version of this expression here. So the lambdas have been lambda of x dot, and then the previous centered dots for application have been replaced by spaces. Okay, so, well, we've been trying to write out lambdas in linear form, but in some cases, in some sense, they're always really trees, just like expressions in the Wolfram language are trees. So here, for example, is this lambda shown as a tree. There it is. There's the lambda. It's got 3 lambdas. The lambdas are positively pink here, and there the thing is written as a tree. The leaves of the tree are the variables. The intermediate nodes are either lambdas or abstraction, i.e. abstractions, or applications, thing applied to thing. The applications are shown here as gray dots. The lambdas are shown as pink boxes. So everything about lambdas can be done in this tree representation. So for example, beta reduction can be thought of as an operation on a piece of the tree representing a lambda. So there's what beta reduction looks like, sort of as a tree operation. But okay, as we talked about before, it never matters what specific names have been given to the variables. All that matters is what lambdas they're associated with. And we can indicate this by overlaying appropriate connections on our tree. So there we have this sort of blank variables down here, and we're saying what the variable is by saying what lambda that variable leaf is associated with this. So these are associated with the y lambda. This one here is associated with the x lambda, and so on. So to find out which lambda a given variable goes with, we just have to count how many lambdas we encounter walking up the tree from the leaf representing that variable before we reach its lambda, so to speak. So this means we can represent the lambda just by filling in a number at each leaf of the tree. And these numbers are precisely the De Bruijn indices that we discussed before. So now we've seen that we can replace our named variables lambda tree with a De Bruijn index lambda tree. So writing this particular tree out as an expression, we get this. The lambdas now don't have any explicit variables specified, but yet the expression is hooked up in the same way it was when we were explicitly using variables. And there's the hookup, so to speak. So once again, we can get rid of our application brackets by using the application operator. And actually, we don't need either the application operators or even the lambdas here. Everything can be deduced just from the sequence of brackets. So in the end, we can write our lambda out as bracket, bracket, 1, 1, close bracket, open paren, 1, 1, open bracket, 2, etc., where there's an implicit lambda before every open bracket character and an implicit application dot between every pair of digits. And yes, we're only dealing with a case where all the De Bruijn indices are below 10. Otherwise, that 1, 1 might be an 11 rather than a 1, application 1. Okay, so now we have a minimal way to write out a lambda as a string of characters. It's compact, but it's hard to decode. So how can we do better? At the very simplest level, we could, for example, color code every character. So here with explicit lambdas and brackets included. But any pure string makes the nesting structure of the lambdas visible only rather implicitly in the sequence of brackets. So how can we make this more explicit? Well, we could explicitly frame each nested lambda. Here's the result from doing that. Or we could indicate the depth of each element, either typographically, like this, or graphically, where the depth here is the tree depth of the expression in Wolfram language. So we can think of this as a kind of one-dimensionally unrolled version of a tree representation of lambdas. Another approach is in effect to draw the tree on a two-dimensional grid to form what we can call a trompe diagram. So to see what's going on here, we can superimpose our standard tree on the trompe diagram. So each vertical line represents an instance of a variable. The top of the line indicates the lambda associated with that variable, with the lambda being represented by a horizontal line. So when one instance of a variable is applied to another, as in, for example, u of v, there's a horizontal line spanning from the u vertical line to the v one. So, for example, here there's one variable, it's being applied to this variable. There's a horizontal line that spans between the vertical line representing that variable and the vertical line representing the next variable. So with that setup, here are some trompe diagrams for a few small lambdas. Well, another graphical approach is to use string diagrams that directly show how the elements of lambdas are wired up. So consider, for example, the very simple lambda, lambda of A, lambda of B, B of A. You can represent this as a string diagram like this, where there's a lambda of A, a lambda of B, the pink nodes, and a single application node. And this is showing kind of the hooking up of things in this lambda expression. So the connectivity of this string diagram is the same as in this diagram here, which is similar to what we showed earlier, showing how the lambdas are hooked up to variables. There's the string diagram, there's the hookup diagram, so to speak. So in the string diagram, on the other hand, the explicit variables have been completely squashed out. We don't even see the variables there, we just see lines. But they're indicated implicitly by which lambdas the lines connect back to. So at each node, at each lambda node, there is one outgoing edge that represents the argument of the lambda. So here it's this outgoing edge here it's this outgoing edge here. And that connects to the body of the lambda. So here it's connecting to this application, and so on. So just as when we represent lambda with a tree, the content of the lambda hangs off the top of the diagram. So, okay, so here are some string diagrams for a few small lambdas. And in these diagrams, the edges that exit the diagram at the bottom correspond to variables that are unused in the lambda. The cups that appear in the diagrams correspond to variables that are immediately used, as in lambda of x comma x. So what do these purple down arrows mean? These strange purple arrows here. Well, for example, that occurs in lambda of A, lambda of B of B of B. It represents the copying of a variable, which is needed here because in that example, where there's a lambda of B, B of B, the B is used twice in the body of the lambda. So if we return to our previous example, now written with explicit variables, here's the somewhat complicated string diagram that corresponds to that expression. With a couple of copies in it, there are the lambdas. We've got the applications as the gray dots. We've got 3 copies, 3 lambdas, bunch of applications. That is this expression as a string diagram. So one can think of a string diagram like this as somehow defining the flow of symbolic content through pipes associated with variables. But is there some purer way to represent such flows without having to introduce variables at all? Well, yes, there is, and it's to use combinators. And indeed, there's an immediate correspondence between combinator expressions and lambdas. So, for example, this lambda expression can be represented in terms of combinators by this expression. And as is typical of combinators, this is in a sense very pure and uniform, but it's also very difficult to interpret. And yes, as we'll talk about later, small lambda expressions can correspond to large combinator expressions, and the same is true the other way around. So that, for example, S of S of K of S becomes, as a lambda expression, this thing here, or in more compact form, this thing here. But okay, this compact form is in a sense a fairly efficient representation, but it has some hacky features. Like, for example, if there are De Broglie indices whose values are more than 1 digit long, they'll need to be separated by some kind of punctuation. But what if we insist on representing a lambda expression purely as a sequence of, let's say, zeros and ones? Well, one thing we can do is to take our compact form that we have here and represent its punctuation characters by fixed strings, and then effectively represents its De Broglie indices by numbers written in unary. So giving, for this example here, we would get this string of zeros and ones. We could get, depending on how we define the punctuation characters, we can get this string of zeros and ones. So this procedure can be thought of as providing a way to represent any lambda by an integer, although it's certainly not true that it associates every integer with a lambda. To make this a sort of a well-delimited integer, we'd have to put a 1 at the beginning so we don't lose the leading zeros. Well, let's talk about enumerating lambdas. So to begin our Ruliological investigation of lambdas and what they do, we need to discuss what possible forms of lambdas there are, or in other words, how to enumerate lambda expressions. So an obvious strategy is to look at all lambda expressions that have progressively greater sizes. But what is the appropriate measure of size for a lambda expression? Mostly here we'll use Wolfram language leaf count. So for example, this lambda expression will be considered to have size 10, because in the most direct Wolfram language tree rendering, which is this, there are 10 leaves. We'll usually render lambdas instead in forms like this, in which case the size is the number of De Broglie index leaves or variable leaves plus the number of lambdas. Well, we could consider alternative measures of size in which, for example, we assign different weights to abstractions, lambdas, and to applications, or to De Broglie index leaves with different values. But using leaf count as our measure, there are then, for example, 14 lambdas of size 4. Here they are. And as trees, these lambdas are like this. Or as Trompe diagrams, they're like this. Well, the number of lambdas grows very rapidly with size. Here's a table. Well, actually, it turns out these numbers can actually be computed from a simple recurrence. Here's the recurrence in terms of bivariate recurrence like this. For large n, the number of lambdas grows roughly like n factorial, though apparently slightly slower. And at size n, the maximum depth of the expression tree is n minus 1. The mean is roughly 3 plus n over 4, and the limiting distribution looks like this. We can also display the actual forms of the lambdas, with a notable feature being the comparative diversity of forms that one sees. So these are the actual visual versions of stacked up lambdas, all the possible lambdas of size 3, size 4, and size 5. Okay, let's talk about the evaluation of lambdas. What does it mean to evaluate a lambda? The most obvious interpretation is to do a sequence of beta reductions until one reaches a fixed point where no further beta reduction can be done. That's so, for example, we might have this lambda at the beginning that undergoes 3 beta reductions to get that lambda at the end. And this is very similar to the evaluation process in Wolfram language, where you're evaluating until you reach a fixed point where there's no further evaluation that can be done. So if one uses De Broglie indices, this beta reduction becomes a transformation of, for lambda of blank, and in this particular case, it becomes this set of transformations here. And in more compact notation, it will become this, while in terms of trees, it becomes this. So by rendering the characters in the De Broglie index form as color squares, we can also represent this evolution in kind of a space-time form like this, going down the page. What about other lambdas? Well, none of the lambdas of size 3 contain the pattern lambda of blank, and so none of them allow beta reduction. At size 4, The same is true of most of the 14 possible lambdas, but there's one exception which allows a single step of beta reduction. Here it is. At size at size 5, 35% of the lambdas aren't inert, but they still have very short. Oh, sorry, that was the beta reduction I was trying to show you. I was trying to show you these were the lambdas of size 3, none of which contain lambda of blank curried of blank. And so they don't undergo beta reduction. But here is an example of size 4 that does have one step of beta reduction that it can do. So at size 5, 30% of lambdas aren't inert, but they have very short lifetimes. The maximum lifetime is only 3 here. So this is the longest evaluation chain of length 3. You can represent that in terms of trees like this. At size 6, 44% of lambdas allow beta reductions and aren't immediately inert. And a couple of lambdas have length 4 evaluation chains. So here are those evaluation chains. And now there's something new, a period 1 looping lambda, or quine, that just keeps on transforming into itself under beta reduction, and so never reaches a fixed point where no beta reduction can be applied. So here's that thing. Just keep applying beta reduction, you keep getting back the same thing again. As a tree looks like this. Size 7, just over half the lambdas aren't inert. There are a couple of self-repeating lambdas. They look like this. This is the first of these is a simple extension of the self-repeating lambda at size 6. The second is something at least somewhat different. So at size 7, there are a couple of cases where there's a small transient before a final repeating state is reached. So here, that's the compact representations of those forms. And here's what happens with lambda trees in this case, where now we've indicated in red the part of each tree that's involved in each beta reduction. Now there's also something new. 3 cases where beta reduction leads to lambdas that grow forever. So the simplest case is this one here, and which grows in size by 1 at each step. As you can see, it's extruding that chain of lambdas at the top. Well, then there is this expression here, which after a single step transient grows in size by 4, by leaf count 4 at each step. Finally, there's this creature, which grows in a slightly more complicated way. And we can see that growth there. We can see it in compact form as trees. We can see it there in terms of tromp diagrams or in terms of a space-time diagram. So it alternates between growing by 4 and by 12 on successive steps, so that at step t, so long as t is larger than 1, where t is the number of steps, it's of size 8t plus 4 mod t plus 1 comma 2. And there's a picture of its size as a function of number of steps. If we look at what's happening here underneath, we see that beta reduction is just repeatedly getting applied to the first lambda at each step. So that's what happens to the expressions. At each step, the first lambda is undergoing beta reduction. And we can conveniently indicate this when we plot the successive sizes of lambdas. So there we are, and those red bars represent the parts of the lambdas that we're showing here, sort of written out in effect vertically, are the parts of the lambdas that are undergoing beta reduction. Okay, at size 8, that was the size 7 lambdas. At size 8, things begin to get more interesting. So of the 43,977 possible lambdas, 55 are not inert. The longest evaluation chain that terminates occurs for that lambda there, and it's of length 12, and we're showing it here. So among those 43,977 size 8 lambdas, there are only 164 distinct patterns of growth. And we can see those are the patterns of growth displayed for each of those, the distinct patterns of growth for all of those lambdas. So the 81 lambdas that don't terminate have various patterns of growth. Here are examples of them. Some, like this lambda here, alternate every other step. They're just periodic. Others, like this lambda here, have period 3. And sometimes, as in this lambda here, there's a mixture of growth and periodicity. So, see, that's showing the growth and periodicity. So we're seeing progressive growth, but it's wiggling back and forth as it grows. So there's also simple nested behavior, as in, that's just an example of this thing wiggling back and forth, I think. There's also nested behavior. No, this is that example. This is an example with nested behavior, which we can see as we look at the successive sizes as a function of number of steps. And the envelope here grows like square root of t. Well, there's more elaborate nested behavior in this example here, where now the envelope of those nested sort of fractal pieces grows linearly with t. Well, finally, in these size 8 lambdas, there is this guy, which shows highly regular 2 to the square root of 2t growth. Well, the conclusion is that for lambdas up to size 8, nothing more complicated than nested behavior occurs. And in fact, in all these cases, it's possible to derive exact formulas for the size at step t. To see roughly how these formulas work, we can start with this sequence here, 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5, 5, etc. And this sequence turns out to be given by the nestedly recursive sequence. I've studied nestedly recursive functions a lot fairly recently. It's given by a nestedly recursive sequence. A of 1 is 1, and A of t is A of t minus 1 plus 1. So the teeth term of this nested recurrence is floor of a half plus square root of 2t. And so for the nested sequence that we talked about that came from lambdas, the corresponding result is this slightly obscure thing here with ceilings of 8t minus 15 and so on. It's remarkable how simple the lambda can be and how complicated the kind of traditional mathematical representation can be. So for the second lambda we just showed, back wherever it was, second one here, the representation, the kind of mathematical style representation for t greater than 3 at least, is this monstrosity here, and involving whiles and comaps and integer exponents and so on. Again, it's a remarkable thing. We're trying to lasso in this basically computational system using mathematical constructs, and this is the kind of thing we get. So for the third example, turns out to be, again, somewhat resolvable but it's still a very complicated thing with ceilings of square roots of 1 plus 8 8 times t minus 2, and so on. It is remarkable that these formulas exist, yet are as comparatively complicated as they are. And in effect, they're taking us a certain distance to the edge of what can be captured with traditional mathematics, as opposed to being findable only by irreducible computation. The world of larger lambdas. So we've looked systematically at lambdas up to size 8. So what happens with larger lambdas? Let's talk about size 9. At size 9, there are 454,283 possible lambdas. Now the distribution of lifetimes is this here. The longest finite lifetime of 55 steps occurs for this little tiny innocuous looking lambda here, which evolves just to lambda of 1 eventually. And here are the sizes of lambdas on each step obtained with that lambda that, as we see, eventually turns into just lambda of 1 after 55 steps. So why does this particular process terminate? Well, it's not easy to see. Looking at the sequence of trees that we generate, here they are, there's some indication of how branches rearrange and then disappear. The array plot isn't very illuminating either. But as is so often the case, it doesn't seem like there's any identifiable mechanism to what happens. It just does. Well, the runner-up for lifetime among length line lambdas with lifetime 44 is this little lambda here, which eventually evolves to this somewhat more complicated lambda, which happens to be the integer 16 in the representation of integers, the Church numeral representation of integers that we talked about before. So, and this is the way that lambda evolves, eventually reaching that fixed point that now isn't just a lambda, something like lambda 1, it's that more complicated lambda form that represents the Church numeral 16. So if we view this in kind of space-time array form, there is at least a hint of a mechanism. We see that over the course of the evolution, there's a steady linear increase in the quantity of pure applications without any lambdas to drive things. That's what this blue and gray section here represents. So, of the 748 size 9 lambdas that grow forever, most have ultimately periodic patterns of growth. The one with the longest growth period, which is 10 steps, is this little innocuous creature here, which has the rather unremarkable pattern of growth that looks like this. And you can see that in terms of trees here. So only 35 lambdas have more complicated patterns of growth. And these are their patterns of growth. Many have behavior similar to what we saw with size 8. There can be nested patterns of growth with an envelope that's linear. For example, in this case here, there can be what's ultimately pure exponential growth, like this case here. There can also be slower but still exponential growth. In this particular case here, it's growth of the form 2 to the square root of 2t. So there's growth that at first looks like it might be complicated, but eventually ends up purely linear. And then there's what might seem to be irregular growth. But taking differences between these sizes, growth sizes, reveals a nested pattern. Even though there's no obvious nested structure in the detailed pattern of lambdas in this particular case. That's the space-time pattern of lambdas that we get in this case. Okay, so that's about it for size 9. Size 10. Well, there are now 5,159,441 possible lambdas, about 5 million lambdas. So of these, 38% are inert, 0.15% of them don't terminate. So here's the distribution of lifetimes. And some examples of lambdas with long lifetimes are these ones here. Some of these terminate with small lambdas. The one up here with lifetime 88 yields a lambda of size 342, while the second one of these lambdas with lifetime 56, first lambda of lifetime 56 goes to a tiny lambda, but the other one of lifetime 56 yields a lambda of size 386. And those are the trees that you get. Those are the sort of before and after, the initial tree and the final tree for these lambdas that terminate. So all of these work in somewhat different ways. In some cases, the behavior looks quite systematic, and it's at least somewhat clear that they'll eventually halt. In others, it's not obvious at all. So there are the space-time diagrams. You can see it's notable that many, though not all of these evolutions, so linearly increasing kind of dead regions over here, for example, and over here, consisting purely of applications without any actual lambdas. So that, for example, so there's no pink there, but there are no lambdas there. So that, for example, the final final fixed point in the lifetime 123 case is this thing here. So what about other cases? Well, there are surprises. Like consider this lambda here. Running this, say, for 2,000 steps, it seems to be just uniformly growing. There it is, up to a few thousand steps. But then suddenly, after 3,779 steps, there's a surprise. It terminates, leaving a lambda of size 4,950. So looking at successive differences in these sizes doesn't give one any obvious advance warning of termination. That at the end, the plot stops because the lambda terminates in its evaluation. But if one looks at the actual sequence of lambdas generated here just for 200 steps, we can see what appears to be the somewhat telltale buildup of dead applications. And indeed, later on, we'll see an even longer-lived example. So even though it's sometimes hard to tell whether the evaluation of a lambda will terminate, there are plenty of cases where it's obvious. An example is when the evaluation chain ultimately becomes periodic. At size 10, there are longer periods than before. Here's an example with period 27. There's also growth where the sequence of sizes has obvious nested structure with a linearly growing envelope. So this is a case of that. And then there's nested structure, but superimposed on 2 to the square root of t growth. That's what happens there. Okay, that was the story of size 10 lambdas. Size 11, we are digging deeper into the jungle of lambdas. At size 11, there are 63 million and change possible lambdas. Most of the behavior one sees looks very much as before, but there are some surprises. So one of those surprises is this creature here. This is its, look at that thing being flat and having little bumps and so on. This is its space-time diagram. Another surprise is this lambda here. And yes, there doesn't seem to be any overall regularity in how this lambda behaves. I'm showing it progressively more steps, 50, 100, 1,000, 2,500 steps here. Nor is there any detailed regularity that shows up in the sequence of actual lambdas that are produced. So far as I can tell, like so many other simple computational systems from Rule 30 on, that fairly simple lambda there, or which we can draw as this tree here, just keeps generating unpredictable behavior forever. Okay, the issue of undecidability. How do we know whether the evaluation chain for a particular lambda, like this one on the screen, will terminate? Well, we can just run for a certain number of steps and see if it terminates by then. And perhaps by that point, we'll see obvious periodic or nested behavior that will make it clear that it won't ever terminate. But in general, we have no way to know how long we might have to wait, how long we might have to run for to be able to determine whether our lambda terminates or not. It's a very typical example of the computational irreducibility that occurs throughout the world of even simple computational systems. And in general, it leads us to say that the problem of whether a given lambda evaluation will terminate must be considered undecidable, in the sense that there's no computation of bounded length that can guarantee to answer the question. But what happens in practice? Well, we've seen just now that at least for sufficiently small lambdas, it's not too hard to resolve the question of termination, but already at size 10, there are issues. So for example, this lambda here, the first 1,000 steps of evaluation lead to lambdas with a sequence of sizes that seem like they're basically just uniformly increasing. Here you go. But, after 10,000 steps, same story, with the size growing roughly like steps t over 3. But if we look at the structure of the actual underlying lambdas, even for just 200 steps, we see that there's a dead region that's beginning to build up. Continuing to 500 steps, the dead region continues to grow more or less linearly. Detrending the sequences of sizes by subtracting t over 3, we get this form here. There's definite regularity here, which suggests that we might actually be able to identify a pocket of computational reducibility in this particular case and be able to work out what will happen without having to explicitly run each step. And yes, in fact, that's true. Let's look again at the form of the lambda we're dealing with. Here it is. The second part turns out to be the Church numeral representation for the number 2. So we're showing that with this green box here. That's and so now we're showing the transformation. The whole lambda evaluates according to that form there that shows the green, this thing here, the lambda of 2 of 2 of 1, that is Church numeral 2, which we're showing as this green 2. And that applying the lambda to that Church numeral, turns out the result can be represented as, when we do this, we can represent the result in terms of applying Church numerals to Church numerals. Well, normally we might think of doing things like arithmetic operations on integers, doing these arithmetic operations, but here we're seeing something different. We're seeing integers, in effect, applied to integers. So, for example, what does this mean? 2 applied to 2, or in explicit lambda form, lambda of 2 of 2 of 1, the Church numeral 2, applied to lambda of 2 of 2 of 1, the Church numeral 2. What does this evaluate to? Well, repeatedly doing beta reduction, it goes through this sequence of steps. Or in other words, what we're seeing is that, we're not seeing it here, but we're seeing that 2 of 2 turns into 4. And boy, okay. So here's some other examples. We're seeing 2 of 2 turns into 4, 2 of 3 turns into 9, 3 of 2 turns into 8. And so how do we recognize what's going on? Well, in general, we're seeing that x of y turns into y to the x. So now we can decode our original lambda expression. So that original lambda expression is that lambda of 1 of 1 of 1 applied to, we can see that that applies to x. That evaluates to x to the x to the x to the x. And so in this particular case, it's lambda of 1 of 1 of 1 applied to Church numeral 2, which is then equal to 2 to the 2 to the 2 squared. Or in other words, if we just do that computation, 65,536. So despite how we might have looked at first, the evaluation of that original lambda we had will eventually terminate, given a lambda of size 655,539. It'll take about 200,000 steps to do this. Curiously, this whole setup is extremely similar to something I studied about 30 years ago in connection with combinator-like systems of the form E of x blank y blank goes to x of y. So it's somewhat remarkable how long it took our simple lambda to terminate. And actually, given what we've seen, it's straightforward to construct lambdas that will terminate, but will take even longer to do so. So for example, let's consider this lambda here that evaluates to the tetration 2 to the 2 to the 2 to the 2 to the 2 n times. And it takes about that many steps to evaluate to that form. So a little while, we'll see how to set up lambdas that can compute not just tetration, but the Ackermann function and any level of hyperoperation, as we can define recursively by this recursive definition, where we're effectively successively nesting operations to apply to other things. So h of 1 here is just plus, h of 2 is times, h of 3 is power, h of 4 is tetration, and so on. Tetration is the 2 to the 2 to the 2, thing to the thing to the thing. Okay, so there are lambdas, and actually even rather simple ones, whose evaluation terminates but only after a number of steps that has to be described with hyperoperations. But what about lambdas that don't terminate at all? We can't explicitly trace what the lambda does over the course of an infinite number of steps. So how can we be sure that a lambda won't terminate? Well, we have to construct a proof. Sometimes that's pretty straightforward because we can easily identify that something fundamentally simple is going on inside the lambda. So, for example, consider this lambda here. The successive steps in its evaluation look like this, with the elements involved in each beta reduction being highlighted. And it's very obvious what's going on here and that it will continue forever. But if we wanted to, we could construct a formal proof of what's going to happen, say using mathematical induction to relate one step to the next. And indeed, whenever we can identify kind of a stem cell-like core generator that repeats, we can expect to be able to use induction to prove that there won't be termination. So there are plenty of other cases that we've seen in which we can tell there's enough regularity, say in the pattern of successive lambdas, that it's basically visually obvious that there won't be termination. And though there will often be many details to wrestle with, one can expect a straightforward path in such cases to a formal proof based on mathematical induction. In practice, one reason visual obviousness can sometimes be difficult to identify is that lambdas can grow too fast to be consistently visualized. The basic source of such rapid growth is that beta reduction ends up repeatedly replicating increasingly large subexpressions. If these replications in some sense form a simple tree, then one can again expect to do induction-based proofs, typically based on various kinds of tree traversals. But things can get more complicated if one starts ascending the hierarchy of hyperoperations, as we know lambdas can. And for example, one can end up with situations where every leaf of every tree is spawning a new tree. So at the outset, it's certainly not self-evident that the process of induction will be a valid way to construct a proof of a statement about infinity, such as that a particular lambda won't ever terminate even after an infinite number of steps. But induction has a long history of use in mathematics, and for more than a century has been enshrined as an axiom in Peano arithmetic, the axiom system that's essentially universally used, at least in principle, in basic mathematics. Induction, in a sense, says that if you always have a way to take a next step in a sequence, say on a number line of integers, then you'll be able to go even infinitely far in that sequence. But what if what you're dealing with can't readily be unrolled into a simple integer-like sequence? For example, what if you're dealing with trees that are growing new trees everywhere? Well, then ordinary induction won't be able to get you to all the leaves. But in set theory, which is typically the ultimate axiom system in principle used for current mathematics, there are axioms that go beyond ordinary induction and that allow the concept of transfinite induction. And with transfinite induction, which can essentially walk through all possible ordered sets, one can reach the leaves in a trees always beget trees type system. So what this means is that while the non-termination of a sufficiently fast-growing lambda may not be something that can be proved in Peano arithmetic, i.e. with ordinary induction, it's still possible to be provable in set theory. Inevitably, though, even set theory will be limited, and there'll be lambdas whose non-termination it can't prove, and for which one will have to introduce new axioms to be able to produce a proof. But can we explicitly see lambdas that have these issues? I wouldn't be surprised if some of the ones we've already considered here might actually be examples, but that will most likely be a very difficult thing to prove. And an easier, but still difficult approach is to explicitly construct, say, a family of lambdas where within Peano arithmetic, there can be no proof that they all terminate. So let's consider some slightly more complicated definitions here. Let me go back to showing that. Okay, so here are some definitions for G of n and f of n. There's recursive definitions, and well, these are actually not even recursing in G and F. F recurses, G does not. The G of n here are so-called Goodstein sequences. for which it's known that the statement that they always reach zero is one that can't be proved purely using ordinary induction, i.e. in Peano arithmetic. Well, needless to say, there's a lambda that's even comparatively simple that has been constructed to compute the lengths of these Goodstein sequences. So feed in a representation of the integer n as a Church numeral, and this lambda will compute a representation of the length of the corresponding sequence g of n, i.e. how many terms are needed to reach zero. This length will be finite if, and only if, the evaluation of the lambda terminates. So, in other words, the statement that all lambda evaluations of this kind terminate is equivalent to the statement that all Goodstein sequences eventually reach zero. But what actually happens if we evaluate lambdas of this kind? Well, here's the result for the first few values of n. And for n equals 1, the process terminates in 18 steps, with the final result, lambda of 2 of 2 of 1, or our representation of the integer 2, reflecting the fact that g of 1 is just the list 1, 0, terminates in 2 steps. For n of 2, after 38 steps, we get the integer 4, reflecting the fact that g of 2 is the list 2 of 2, 2, 1, 0. For n of 3, many more steps are needed, but eventually the result is 6, reflecting the fact that g of 3 is 3, 3, 3, 2, 1, 0. What about n equals 4? We're seeing the beginnings of the n equals 4 computation in terms of lambdas. Well, it's known this process must eventually terminate in this case as well, but it may take a very long time, since the final result is known to be 3 times 10 to the 402 million and something minus 1. If we keep going, the sizes and corresponding times rapidly get still much, much larger. Well, this certainly isn't the only way to escape provability by Peano arithmetic, but it's an example of what this can look like. We should remember that in general, whether the evaluation of a lambda ever terminates is a question that's fundamentally undecidable, in the sense that no finite computation whatsoever can guarantee to answer it. But the question of proving, say, that the evolution of a particular lambda doesn't terminate is something different. If the lambda wasn't generating much novelty in its infinite lifetime, say it was just behaving in a repetitive way, then we'd be able to give a fairly simple proof of its non-termination. But the more fundamentally diverse what the lambda does, the more complicated the proof will be. And the point is that essentially as a result of computational irreducibility, there must be lambdas whose behavior is arbitrarily complex and diverse. But in some sense, any given finite axiom system can only be expected to capture a certain level of diversity, and therefore to prove non-termination only for a certain set of lambdas. To be slightly more concrete, we can imagine a construction that will lead us to a lambda whose termination can't be proved within a given axiom system. It starts from the fact that the computation universality of lambdas implies that any computation can be encoded as the evaluation of some lambda. So in particular, there's a lambda that systematically generates statements in the language of a given axiom system, determining whether each of those statements is a theorem in their axiom system or not. And we can then set it up so that if ever an inconsistency is found in the sense that both a theorem and its negation appear, then the process will stop. In other words, the evaluation of the lambda is in a sense systematically looking for inconsistencies in the axiom system, terminating if it ever finds one. So this means that proving the evaluation of the lambda will never terminate is equivalent to proving that the axiom system is consistent. But it's a fundamental fact that a given axiom system can never prove its own consistency. It takes a more powerful axiom system to do that. That's basically Gödel's second incompleteness theorem. So this means that we'll never be able to prove that the evaluation of the lambda we've set up terminates, at least from within the axiom system that it's based on. So in effect, what's happened is that we've managed to make our lambda in its infinite lifetime scan through everything our axiom system can do, with the result that the axiom system can't go further and say anything bigger about what the lambda does. It's a consequence of the computation universality of lambdas that it's possible to package up the whole metamathematics of our axiom system into the infinite behavior of a single lambda. But the result is that for any given axiom system, we can in principle produce a lambda where we know that the non-termination of that lambda is unprovable within that axiom system. Of course, if we extend our axiom system to have the additional axiom, this particular lambda never terminates, then we'll trivially be able to prove non-termination. But the underlying computation universality of lambdas implies, in analog of Gödel's theorem, that no finite collection of axioms can ever successfully let us get finite proofs for all possible lambdas. And yes, while the construction we outlined gives us a particular way to come up with lambdas that escape a given axiom system, those certainly won't be the only lambdas that can do it. What will be the smallest lambda whose non-termination is unprovable in, say, Peano arithmetic? The example we talked about just now, based on Goodstein sequences, is already quite small, but there are no doubt still much smaller examples. Though in general, there's no upper bound on how difficult it might be to prove that a particular lambda is indeed an example. If we scan through all possible lambdas, it's inevitable that we'll eventually find a lambda that can escape from any possible axiom system. And from experience in the computational universe, we can expect that even for quite small lambdas, there'll be rapid acceleration in the size and power of axiom systems needed to rein them in. Yes, in principle, we can just add a custom axiom to handle any given lambda, but the point is that we can expect that there'll quickly be, in a sense, arbitrarily small leverage. Each axiom added will cover only a vanishingly small fraction of the lambdas that we reach. Okay, let's talk about numerically interpretable lambdas. So far we've discussed the evaluation of lambdas on their own. But given a particular lambda, we can always apply it to input and see what it computes. Of course, the input itself is just another lambda, so a lambda applied to input is just a lambda applied to a lambda, which is itself a lambda. And so we're basically back to looking at lambdas on their own. But what if the input we give is something interpretable, say a lambda corresponding to an integer? In the representation that we used above, we could use that for an integer. So a lambda applied to such a thing, a representation of an integer, will, assuming it terminates, inevitably just give another lambda. Most of the time, that resulting lambda won't be interpretable, but sometimes it can be. So, for example, let's look at the following. Let's look at this lambda here. Here's what happens if we apply that lambda. If we apply that lambda to a sequence of integers represented as lambdas. Okay, so that's that lambda. We're calling it f here, applied to a sequence of integers. So f of 1 eventually evaluates to the integer 3, f of 2 evaluates to 8, 3 evaluates to 15, and so on. So in other words, this lambda can be interpreted as, in fact, as implementing a numerical function from integers to integers, this particular case, the function 2n plus n squared. So every time f of 2, 2n plus n squared gives 8 in that case, f of 4, 2n plus n squared gives 24, and so on. So what kinds of such numerical functions can lambdas represent? Insofar as lambdas are capable of universal computation, they must in the end be capable of representing any integer function, but the necessary lambda could be very large. So early on, we saw a constructed representation for the factorial function as a lambda. Here it is. We also know that if we take the Church numeral lambda that represents an integer m and apply it to the lambda that represents an integer n, we get the lambda representing n to the m. It's then straightforward to construct a lambda that represents any function that can be obtained as a composition of powers. So here are some examples of lambdas that represent compositions of powers. All right. Let's go back and talk about, go back a little bit. So I was talking about, I'm talking about interpretable lambdas, where you can apply a lambda to a sequence of lambdas represented in um, in terms of that represent integers. So, for example, here we have that particular lambda applied to a sequence of lambdas representing integers. And what we discover is that we're always getting something of a form. Let's say f of 3 is transformed to 15 and so on. And so in this particular case, we're representing the function n goes to 2n plus n squared. And so that is a way where we're representing a numerical function in terms of lambdas. We can represent all kinds of numerical functions in terms of lambdas. In fact, ultimately any numerical function in terms of lambdas, but the lambdas might have to be quite big. We saw before the lambdas representing a factorial. That's the form of that. So we also saw that applying effectively the representation of integers to the representation of integers gives powers. And so that means we can rather easily construct lambdas that represent any composition of powers, things like this. And the same is true for that we can do that for tetration and other higher hyperoperations. So, for example, this lambda here, very innocuously looking lambda here, gives a diagonal of the Ackermann function. So this tiny little lambda, if we apply it to successive Church numeral integers, gives the succession of integers that is of this form: 1, 3, 7, 61, looking really good, and then 2 to the 2 to the 2 to the 16 minus 3. What about lambdas in the wild? How often will they be numerically interpretable, and what kinds of functions will they represent? Among size 5 lambdas, for example, 10 of 82, or about 12%, are interpretable and represent the functions 0, 1, n, and n squared. Among size 10 lambdas, the fraction that interpretable falls to about 4%, and the frequency with which different functions occur is something like this. So we see the function n is most common, n to the n is second most common, and so on. The least common in this collection is the constant function 6. So looking at lambdas of successively greater size, here are some notable firsts of where functions appear. And yes, we can think of the size of the minimal lambda that gives a particular function to be sort of the algorithmic information content of that function with respect to lambdas. Well, needless to say, there are some other surprises, like particular lambda bracket bracket 2 to bracket 1, which gives 0 when fed any integer as input, but takes an super exponentially increasing number of steps to do so. Here's that lambda shown with successive Church numeral inputs showing its evaluation. Well, we've been discussing what kind of numerical functions can be computed by what lambdas, but another question we can ask is how much time, i.e. how many beta reductions such computations will take, or how much space they'll need for intermediate expressions. And indeed, even if the outputs are the same, different lambdas can take different computational approaches and different computational resources to reach those outputs. So for example, among size 8 lambdas, there are 41 that compute the function n squared, and here are the sizes of intermediate expressions, all plotted on the same scale, generated by running these lambdas for the input that is the integer 10 represented as a Church numeral. So these pictures suggest that these various lambdas have a variety of different approaches to computing n squared. Some of these approaches take more memory, i.e. size of intermediate lambdas, than others. In addition, some take more time, as we can see by the length of the sequences here, than others. So for this particular set of lambdas, the time required always grows essentially just linearly with n, though at several different possible rates. But in other cases, different behavior is observed, including some very long run times. And indeed, in general, one can imagine building up a whole computational complexity theory for lambdas, starting with these kinds of empirical Ruliological investigations. So everything we've discussed here so far is for functions with single arguments, but we can also look at functions that have multiple arguments, which can be fed to lambdas in curried form. In other words, f of x of y. And with this setup, there are lambdas that give x times y. There are other lambdas that give x times y cubed. They're still very tiny lambdas. Okay. Let's talk about multiway graphs for lambda evaluation. So let's say you're evaluating a lambda expression like this. You want to do beta reduction, but which one? For this expression, there are three possible different results, three possible beta reductions that can be done. So in everything we've done so far, we've always assumed that we use the first beta reduction at each step, where we'll discuss what we mean by first in a moment. But in general, we can look at all possible paths of evaluation and form a multiway graph from them. So here we've got that multiway graph, and let's see. So that's showing all possible paths of evaluation from that initial lambda. This is one path, this is another path, and so on. Those are the three possibilities we saw at the beginning. Okay. So our standard evaluation process, in this case, will lead us down that path. We get this path by picking at each step the leftmost, outermost possible beta reduction, i.e. the one that involves the highest relevant lambda in the expression tree and the leftmost one if there's a choice. So this is that computation. But in the multiway graph, we could have picked any path and still ended up at the same final result. Indeed, it's a general property I mentioned of lambdas, the so-called confluence or Church-Russell property, that all evaluations of a given lambda that terminate will terminate with the same result. And we can see that in this case here, all the different paths lead down to that one lambda of one expression at the end. Well, let's see. Here's the version of that multiway graph with the lambdas rendered in tree form. Well, okay, so at size 5, we just look at tiny lambdas. All lambdas give trivial multiway graphs that involve no branching, so things like this. And something that happens too, the looping lambda gives a multiway graph that, let's see, what is it? In which there's a loop. Where is my looping lambda? The looping lambda has been lost. That's one of those things one might say, the looping lambda is lost. It's just a loop in this diagram that returns to a single node. Okay, at size 7, many distinct topologies of multiway graphs start to appear. Let's just see. Oh, there's the looping lambda. I got this. So wait a minute. This is these are these are size 6 lambdas where there is some branching and some merging, and then there's also the looping lambda. And now at size 7, there are a whole variety of topologies of multiway graphs. The numbers underneath are the multiplicities. And mostly these lead to termination. The biggest one of these just has 12 nodes in it. But then there are cases that loop, like these ones here. And finally, there's this little creature here, where something new happens. The multiway graph has many distinct branches. So after 5 steps, the multiway graph looks like this, where the size of each node indicates the size of the lambda it corresponds to, and the pink nodes indicate lambdas that can be further beta reduced. So after just one more step, the multiway graph looks like this. And after another step in a hyperbolic rendering, this is what it looks like. That's where it started up there. So in this particular case, no branch ever terminates. And the total size of the multiway system increases in successive steps like this. Okay, with size 8 lambdas, the terminating multiway graphs can be larger. In that first case, the 124 nodes in the terminating multiway graph, but it still terminates at that node at the bottom. And there are all sorts of new topologies for non-terminating cases, like these. Remember, the pink nodes are ones where there are still unresolved beta reductions. So these graphs are what one does by doing 5 successive beta reductions. The ones that end in loops won't change if we do more reductions. They'll still look the same. But the ones with nodes that with sort of hanging nodes will can do more reduction. In most cases, one ends up with a progressively increasing number of reductions that can be done, often exponential. But here's an example where there are just linearly many 2n minus 1 new reductions that can be done at step t. Meanwhile, sometimes the number of unresolved reductions just remains constant. Like in this case, there are just 4 unresolved reductions. So we know that if there's a fixed point to beta reductions, it's always unique. But can there be both a unique fixed point and branches that continue forever? Turns out that there can. And the first lambda for which this happens is this one, little tiny innocuous lambda here. So with our standard evaluation method, this lambda terminates in 5 steps at lambda of 1, but there are other paths that can be followed that don't terminate, as indicated by those pink nodes at the end. This is unrolling the graph for successive steps. And in fact, in this particular case, at step t, the number of paths, the number of unresolved paths, is given by a Fibonacci-like recurrence and grows asymptotically like the golden ratio to the t. With size lambdas, there's a much simpler case where the termination, non-termination phenomenon occurs. It's this lambda here, and we can see there's a multiway graph where there's one terminating node here, and there's another node here that does not terminate and continues the multiway graph. So in this case, we can run that multiway graph longer. We'll see there's just one kind of extruded piece that comes from the unresolved beta reduction of that single node. Well, there's another lambda here in the menagerie of lambdas, where there's alternation between 1 and 2 non-terminating paths on successive steps. And another where there are asymptotically exactly 5 non-terminating paths. Okay, so some lambdas have very bushy or infinite multiway graphs and some don't. How does this correlate with the lifetimes we obtain for these lambdas through our standard evaluation process? So here's a plot of the size of the multiway graph versus the lifetime for all finite lifetime size 8 lambdas. In orbit, the one case that we talked about before, indicated here with that pink arrow, the multiway graphs are of finite size, and we see some correlation between the size of the multiway graph and the lifetime obtained with our standard evaluation process. And although it's worth noting that even the lambda that with the longest standard evaluation lifetime, which is 12 in this case, still has a fairly modest 27-node multiway graph that looks like this. While the longest finite multiway graph with 124 nodes occurs for a lambda with standard evaluation lifetime 7. So we see that's that point there. So at size 9, here are the multiway graphs for the 10 lambdas that we looked at earlier, that with the longest standard evaluation lifetimes, and these pictures have been computed to 5 steps. So in the standard evaluation lifetime 17 cases, the multiway graph is finite. So these are ones down here that when we actually run that for enough steps, we find out that the multiway graph actually terminates, it's finite. But in all other cases that we looked at here, the graph is presumably infinite. And for example, in the lifetime 55 case, we see at the beginning there, the number of nodes at step t in the multiway graph grows like this, grows very rapidly. But somehow, among all these different paths, we know that there's at least one path that terminates, at least after 55 steps, to give lambda of 1. Sort of a remarkable thing that happens. Okay, let's talk about different evaluation strategies. So the multiway graph shows us all possible sequences of beta reductions for a lambda. Our standard evaluation process picks one particular sequence by having a certain strategy for choosing at each step what beta reduction to do. But what if we were to use a different strategy? So as an example, let's consider this lambda. There turn out to be 4 possible positions at which beta reductions can be done, where the positions can be specified here using Wolfram language conventions. So our standard evaluation strategy does the beta reduction that's listed first here. But how exactly does it determine that that's the reduction it should do? Well, it looks at the lists of 1s and 0s that specify the positions of each of the possible reductions in the lambda expression tree. Then it picks the one with the shortest position list, sorting position lists lexicographically if there's a tie. In terms of the structure of the tree, this corresponds to picking the leftmost outermost beta reduction, i.e. the one that in our rendering of the tree is the highest and furthest to the left. Here it is. So what are some other strategies we could use? One way we can specify a strategy is by giving an algorithm that picks one list out of any collection of lists of 0s and 1s that, so for now, we'll consider only sequential strategies that pick out a single position list, i.e. a single reduction at a time. But another way to specify a strategy is to define an ordering on the expression tree, then to say that the beta reduction will do the one that we reach first if we traverse the tree in that order. And so, for example, our leftmost outermost strategy is associated with a breadth first traversal of the tree. Another evaluation strategy is leftmost innermost, which is associated with a depth first traversal of the tree and a purely lexicographic ordering independent of length of all tree positions of beta reductions. In the Wolfram language, the option tree traversal order gives detailed parameterizations of possible traversal orders for use in functions like tree map, and each of these orders can be used to define an evaluation strategy for lambdas. The standard replace all /dot operation applies to expression trees in the Wolfram language. Also defines an evaluation strategy, which turns out to be exactly our standard outermost leftmost one. Meanwhile, using standard Wolfram language evaluation, after giving an assignment like lambda of x blank, y blank, colon equals whatever, that would be a definition for beta reduction, that yields the leftmost innermost evaluation strategy, since at every level the head lambda of whatever is evaluated before the argument. If the lambda had a hold attribute, then we'd instead get what we can call applicative order, in which the arguments are evaluated before the body. And yes, this whole setup, the arguments of the lambda, that is, are evaluated before the body. This whole setup with possible evaluation strategies is effectively identical to what I talked about some length for combinators a few years ago. Okay, so what happens with different strategies? Well, here are some examples of the evaluation chains generated in different cases. Each of these corresponds to following a different path in the multiway graph. So here are the paths in the multiway graph corresponding to those strategies. In effect, each corresponds to a different way to reach the final result. So if we look at if we plot just the sizes of lambdas obtained at each step, we see that different strategies have different profiles. Notably, in this case, with the standard strategy taking more steps to reach the final result than, for example, depth first. Okay, but so what exactly do these strategies mean? In terms of Wolfram language function tree traversal order, they are the following, although applicative is involves dependency on whether an element is a lambda or an application works slightly differently. In terms of tree positions, these correspond to the orderings, these particular orderings for standard, depth first, etc., which correspond to these paths through the nodes of a tree. That's the traversal order of the tree that gives the ordering that defines which beta reduction to do. So as we talked about a while ago, it's a general feature of lambdas that if the evaluation of a particular lambda terminates, then the result obtained must always be the same, independent of the evaluation strategy used. In other words, if there are terminating paths in the multiway graph, they must all converge to the same fixed point. Some paths may be shorter than others, representing the fact that some evaluation strategies may be more efficient than others. We saw one example of this above, but the differences can be much more dramatic. For example, there's one lambda that takes 74 steps to terminate with our standard evaluation strategy, but only 10 to terminate with depth first evaluation. And there are the traces of that particular lambda and its evaluation. And in fact, it's fairly common to see cases where standard evaluation and depth first produce very different behavior. Sometimes one is more efficient, sometimes it's the other. But despite differences in how one gets there, the final fixed point results are inevitably always the same. But what happens if only some paths in the multiway graph terminate? That's not something that happens with any lambdas up to size 8. But at size 9, for example, there's a lambda that terminates with standard evaluation, but not with depth first. Here's how that works. And so with standard evaluation, we happily get down to this termination point. But with depth first evaluation, we get stuck on this non-terminating node here. And we can see that also in the growth of the number of the size of the lambda expressions that we get with depth first here. So an even simpler example is this one here. With standard evaluation, we go to the terminating node, but with depth first evaluation, we go to the looping node there. So in both these cases, standard evaluation leads to termination, but depth first evaluation does not. And in fact, it's a general result that if termination is ever possible for a particular lambda, then our standard leftmost outermost evaluation strategy will successfully achieve it. But what if termination is never possible? Different evaluation strategies can lead to different behaviors. For example, here's a lambda that can get stuck in a loop of either period 1 or period 2. And it's also possible for one strategy to give lambdas that grow forever and another to give lambdas that are say, periodic in size. So there's standard evaluation. The thing grows in that sort of nested way. With depth first evaluation, it becomes periodic. So there are two different ways of not terminating. But what if one has a whole collection of lambdas? What generically happens? Within every multiway graph, there can be a fixed point, some number of loops, and some tree-like unbounded growth. Every strategy defines a path in the multiway graph, which can potentially lead to any of these possible outcomes. It's fairly typical to see one type of outcome be much more likely than others, and for it to require some kind of special tuning to achieve a different type of outcome. So, for example, for this case here, almost all evaluation strategies lead to termination, except the particular strategy based on what one might call layout order. So, which is that one shown on the tree there. So what happens if we use a strategy where each step we just pick between different possible beta reductions at random with equal probability? Here are some examples for a particular lambda that we talked about above that takes 74 steps to terminate with our standard evaluation strategy. There's quite a diversity of the shapes of curves generated, but it's notable that no non-terminating cases are seen, and that termination tends to occur considerably more quickly than with standard evaluation, which took 74 steps. In fact, the distribution of termination times only just reaches the value 74 seen in the standard evaluation case. So for lambdas whose evaluation always terminates, we can think of the sequence of sizes of expressions generated in the course of their evaluation as being sort of pinned at both ends. When the evaluation doesn't terminate, the sequences of sizes can be wilder. So so that happens in these particular cases of a couple of lambdas here. Those are the different different sequences of evaluation sizes with random choices of which beta reduction to do. Okay, let's talk about the equivalence of lambdas. So consider these lambdas here. They each have a different form, but they all evaluate to the same thing, lambda of 1. And particularly if we're thinking about lambdas in a mathematically oriented way, this means we can think of all these lambdas as somehow representing the same thing, and therefore we can consider them equivalent. Out of all 18 lambdas up to size 4, these 3 are actually the only ones that are equivalent in this sense. So that means there are 15 evaluation inequivalent lambdas up to size 4. Up to size 5, there are a total of 100 forms of lambdas, which evolve to 68 distinct final results. And there are 4 multi-lambda equivalence classes, which are these. And we can summarize that graphically as those are the equivalence classes, just stacking the lambdas on top of each other. Up to size 6, there are a total of 679 forms of lambdas, which evolve to 392 distinct final states, along with 1 looping lambda. And there are 16 multi-lambda equivalence classes, these ones here. If we look at only at lambdas whose evaluation terminates, then we have the following. So for large sizes, the ratio conceivably goes more or less exponentially to a limiting fixed value of around a quarter. Okay, this is only for lambdas that terminate. So what can we say about equivalences between lambdas that don't terminate? Well, it depends on what we mean by equivalence. One definition might be that 2 lambdas are equivalent if somewhere in their evolution they generate identical lambda expressions, or in other words, there is some overlap in their multiway graphs. If we look up to size 7, there are 8 lambdas that don't terminate, and there's a single, rather simple correspondence between their multiway systems up here. These are the multiway systems for all lambdas that don't terminate. Up to size 8, there are 89 lambdas. Excuse me 1 second. Okay, so anyway, up to size 8, 89 lambdas whose evaluation doesn't terminate. And among those lambdas, there are actually many correspondences. So an example of such a correspondence is this one here, of equivalence between that lambda there and that lambda there, and so on. But these are different initial lambdas. So a more elaborate example, here's a more elaborate example where different multiway graphs have overlaps that we can see in the sort of merged color there. So in the first 2 cases here, the overlap is at a looping lambda. In the third case, it's at a series of lambda expressions that we can see down here. So if we look at all 89 non-terminating lambdas, we can look at sort of all the 434 overlapping pairs between these. These correspond to equivalences between lambdas, and there are several subtleties here. First, whether 2 lambdas are seen to be equivalent can depend on the evaluation strategy one's using. For example, a lambda could terminate for one strategy, but can miss the fixed point with another strategy that fails to terminate. In addition, even if the multiway graphs for 2 lambdas overlap, there's no guarantee that that overlap will be found with any given evaluation strategy. And finally, as so often, there's an issue of undecidability. Even if lambda is going to terminate, it can take an arbitrarily long time to do that. And worse, if one progressively generates the multiway graphs for 2 lambdas, it can be arbitrarily difficult to see if they overlap. So determining a single evaluation path for a lambda can be computationally irreducible. Determining these kinds of overlaps can be multi-computationally irreducible. All right, let's talk about causality for lambdas. We're getting through what I've figured out about lambdas. We can think of every beta reduction in the evaluation of a lambda as an event in which certain input is transformed to certain output. If the input from one event V relies on output from another event U, we can say that V is causally dependent on U. Or in other words, the event V can only happen if U happened first. If we consider a lambda evaluation that involves a chain of many beta reductions, we can then imagine building up a whole causal graph of dependencies between beta reduction events. So, simple example, consider this evaluation chain where we've explicitly shown the beta reduction events in yellow. And in this particular case, we've avoided renaming variables that appear. So the blue edges here show how one lambda transforms to another as a result of an event here. The dark red edges show the causal relations between events. Each of them can be thought of as associated with a sub-expression that is the carrier of a causality from one event to another. Keeping only events and causal edges, the causal graph for this particular evolution is what's shown here. If we follow a sequence of causal edges, we get a time-like chain of events that must occur in order. But to traverse transverse to that, we have in the language of posets an anti-chain consisting of what we can think of as a space-like separated events that can occur in parallel. So in this particular case, the first event, i.e. the first beta reduction, leads to this particular expression, in which there are 2 reductions that can be done for lambda of B and for the first lambda of C, but these reductions are completely independent of each other. They can be thought of as space-like separated. So in our standard evaluation scheme, these events occur in a definite order, but what the causal graph shows is that the result we get doesn't require that order, and indeed allows these events to occur in parallel. Many lambdas don't allow parallelization in their evaluation, so have simple linear causal graphs like these. But it's common to have simple branching in the causal graph associated with pieces of the lambda expression that are completely separated as far as beta reduction is concerned, and that can be evaluated separately. One tricky issue that arises in constructing causal graphs for lambdas is figuring out exactly what is really dependent on what. In this case, it might seem that the 2 events are independent, since the first one involves lambda of A and the second one involves lambda of B. But the second one can't happen until the lambda of B is activated by the reduction of lambda of A in the first event, with the result the second event must be considered causally dependent on the first, as one can record in this causal graph here. So while many lambdas have simple linear or branched causal graphs, plenty have more complicated structures. So here are some examples for lambdas that terminate. Lambdas that don't terminate have infinite causal graphs. But what's notable here is that even when the evolution, as visualized in terms of a sequence of sizes of lambdas, isn't simple, the causal graph is still usually quite simple and repetitive. And yes, in some cases, seeing this may well be tantamount to a proof that the evolution of the lambda won't terminate. But a cautionary point is that even for lambdas that do terminate, we saw above that their causal graphs can still look essentially repetitive right up to when they terminate. Let's talk about multiway causal graphs. The causal graphs we talked about just now are all based on analyzing causal dependencies in specific lambda evaluation chains generated with our standard leftmost outermost evaluation scheme. But just like in our physics project, it's also possible to generate multiway causal graphs in which we show causal connections between all states in the multiway graph representing all possible evaluation sequences. So here's a multi-way version of the first causal graph we looked at before. And so the some sort of causal graphs remain linear even in the multi-way case, but that's the multi-way causal graph including states. This is the multi-way causal graph alone, just the causal parts of it. Others, so some of them remain kind of all connected, others split into many paths. It's fairly typical for multi-way causal graphs to be considerably more complicated than ordinary causal graphs. So for example, while the ordinary causal graph for a little lambda is this thing here, the multi-way version of that is this thing here. While the multi-way graph for states, in this case, just looks like this. So yes, it's possible to make multi-way causal graphs for lambdas, but what do they mean? It's a somewhat complicated story, which I won't talk about here because it's basically the same as the story for combinators, which I talked about several years ago. Though lambdas don't allow one to set up the kind of shared subexpression DAGs we considered for combinators, the variables or de Bruijn indices in lambdas effectively lead to long-range correlations that prevent the kind of modular tree-like approach we used for combinators. Let's talk about the case of linear lambdas. So we've seen that in general, lambdas can do very complicated things, but there's a particular class of lambdas, the linear lambdas, that behave in much simpler ways, allowing them to be rather completely analyzed. A linear lambda is a lambda in which every variable appears only once in the body of the lambda. So that means that lambda of a comma a is a linear lambda, but lambda of a comma a of a is not. So the first few linear lambdas are these things here, lambda of a of a, lambda of a, lambda of b comma a of b, because a and b are just occurring once here, and so on. So in de Bruijn index form, those are the linear lambdas. Those are the first few linear lambdas. So linear lambdas have the important property that on beta reduction, they can never increase in size. So without multiple appearances of one variable, beta reduction just removes subexpressions and can never lead to the replication of a subexpression. So indeed, at every step in the evaluation of a linear lambda, all that ever happens is that at most one lambda is removed. So since linear lambdas always have one variable for each lambda, so these are transformations for linear lambdas. So since linear lambdas always have one variable for each lambda, their size is always an even number. And the number, this is the number of linear lambdas compared to the total number of lambdas as a function of the size of the lambdas. So asymptotically, the number of linear lambdas of size 2m grows like 3 times 6 to the m factorial. So here are Trump diagrams for size 6 linear lambdas. So evaluation always terminates for a linear lambda. The number of steps it takes is independent of the evaluation scheme and has a maximum equal to the number of lambdas. The distribution for size 6 linear lambdas is this here. And the multiway graphs for linear lambdas are rather simple. Since every lambda is independent of every other, it never matters in what order they are reduced. And the multiway graph consists of a collection of diamonds, like this one, for example. So every branch has a merge immediately following it. So for size 6 lambdas, the possible multiway graphs with their multiplicities are just these here. For size 8, these are the possible multiway graphs, where that last graph can be drawn in a more obviously symmetrical way like this. For size 10, here are the multiway graphs. And that's the structure. It's quite simple, and there are all sorts of things you can say about it. So in addition to looking at linear lambdas, we can also look at affine lambdas, which are defined to allow 0 as well as 1 instance of each variable. So the affine lambdas behave in very similar ways to the linear lambdas, except that now there are some sort of degenerate diamond structures in the multiway graph like these ones. All right, let's talk about lambdas versus combinators. So now that we've explored all this Ruliology for lambdas, how does it compare to what I found several years ago for combinators? Many of the core phenomena are certainly very much the same, and indeed it's easy to convert between lambdas and combinators, though a lambda of one size may correspond to a combinator of a very different size. For example, the size 4 lambdas have these equivalent combinators. And I think I maybe have found some smaller ones here now. While the size 3 combinators have these equivalent lambdas. Well, not surprisingly, the leaf count size of lambdas tends to be slightly smaller than for equivalent combinators because the presence of de Bruijn indices means lambdas effectively have a larger alphabet to work with. But in the end, lambdas and combinators can do all the same things, just like in these are examples of correspondences between the notable lambdas and notable combinators. The principle of computational equivalence implies that at a fundamental level, the Ruliology of systems whose behavior is not obviously simple will be at least at some level the same. But lambdas have definitely given us some unique challenges. First, there's the matter of variables and the non-locality they imply. It's not like in a cellular automaton or a Turing machine, where, in a sense, every update happens locally, nor is it even like combinators, where things are local, at least on a tree, or hypergraph rewriting systems, where things are local where things are local on a hypergraph. Lambdas are both hierarchical and non-local. Lambda expressions have a tree structure, but variables knit pieces of this tree together. So they can knit them pieces together in sort of arbitrarily complex ways. And beta reduction can, in effect, pull on arbitrarily long threads. All of this then gets entangled with another issue. Lambdas routinely can get very big. And even that wouldn't be such a problem if it wasn't for the fact that there's no obvious way to compress what lambdas do, with the result that even though the Wolfram language gives one a very efficient way to deal with symbolic structures, the things I've done here and talked about here have often challenged my computational resources. Still, in the end, we've managed to do at least the basics in exploring the Ruliology of lambdas and have seen that yet another corner of the computational universe is full of remarkable and surprising phenomena. I first wondered what lambdas might be like in the wild back at the beginning of the 1980s. And I'm pleased that finally now, so many years later, I've finally been able to get a sense of the world of lambdas and both the uniqueness and sameness of their Ruliology. Well, that's the end of what I wrote. In the case of combinators, I produced a rather complete bibliography of what's been written about combinators. Even more has been written, much more has been written about lambdas over the past 90 years, but most of the focus has been sort of formal and theoretical, not empirical and Ruliological. It's this is the idea of doing Ruliology of this kind is something that is very much in my path of doing science and hasn't really been seen elsewhere. All right, well, that was a bit of a marathon, but if people have questions, I'd be happy to try to address them. Let's see, Raum asks, do you think lambda calculus still has a role to play in uncovering how the universe works, or has it mainly served as a stepping stone towards newer rule-based systems? I think you learn a little bit more about the computational universe from every kind of Ruliology you do. From combinators, I learned a bunch of things about the subaxiomatic level of mathematics. You can do the same thing with lambda calculus. in mathematics, we usually talk about axioms and we talk about, x plus y is y plus x, but there's a sub-axiomatic layer that goes down to the level of individual combinators or individual lambdas. And seeing that structure sort of tells us the sub-axiomatic level of mathematics. And insofar as now that we understand things about the Ruliad, we can see that the foundations of mathematics are really the same foundations as the foundations of physics. I think it's useful in interpreting what happens in mathematics to be able to see this kind of sub-axiomatic layer. So I think that the particular details of how we represent the universe in terms of hypergraphs and so on are much more easily dealt with in hypergraphs rather than in this kind of tree-like lambda expressions and so on. I still think that lambda expressions provide sort of a bridge potentially between what is interpretable by us humans and what is out there in the computational universe. I mean, I will also say that in exploring the Ruliad, there are many bases for the Ruliad. The Ruliad is the entangled limit of all possible computations. We can represent those computations in terms of Turing machines, in terms of combinators, in terms of lambda expressions. I've done a little bit now on looking at the Ruliad in the lambda expression basis, in the lambda basis, and I think there may be some interesting things that can be found there. Also in the Turing machine basis, the hypergraph basis, these are all different bases for what is fundamentally the Ruliad. Now, which basis is the best basis to use? Well, that depends on how you're observing the Ruliad. How you're observing the Ruliad also determines the laws of physics that you attribute to the universe. And so there is a basis that is the natural basis for attributing the laws of physics that we attribute to the universe to the Ruliad, so to speak. My guess is that hypergraphs are a pretty good natural basis for what we need to do in physics. I think combinators and lambda calculus are probably a more natural basis for the things we have to do in mathematics. Interesting question. What's the right basis for things like biology? I think there cellular automata seem to be a pretty good basis for exploring the Ruliad, but I don't know for other cases. For example, as we start looking at other kinds of questions in, let's say, neuroscience or other areas where we can apply thinking in terms of the Ruliad, I don't know what the best basis will be. And having this sort of inventory of bases that we've studied, like cellular automata, like multiway, like hypergraph rewriting, like combinators, like Turing machines, having that broad range of different bases for the Ruliad, I think is very useful. Question from Bob. What's the smallest lambda that reduces to each church numeral up to 10? That is a very reasonable question, which I do not think I have explicitly answered. I did answer that question for combinators. I don't think I've answered that question for lambdas. Just go figure it out. It's there's a nice function that is in the lambda packlet that finds a minimal lambda expression for something, and you could do that with by just starting with the church numerals. I don't know the answer. I actually might be able to pull up the answer for combinators, maybe. Let's see if I can in just a moment here. Let's see if I can find that. If I'm lucky, I could get it reasonably quickly. Let me see. I think this might be it. Let's try this. Let me share again. Oh boy. Oh, one moment. We are going to share again. And you see if this is that. So what is this? This isn't quite the right thing. Thought this was the right thing. Let me see here. Maybe that's not quite the right thing. Hold on one second. Oh, here we go. That's again not quite the right thing, but this is a similar kind of idea. This is asking what you need to do to get these, I think, the smallest combinator expressions that reach certain forms. No, so this isn't exactly answering that question, I'm afraid. Something to do to compute with. Maybe I am. Let me not distract here and actually do the computation, but we probably could. Memes is asking, is there a notion of a fixed point in the Ruliad? Well, there are local fixed points in the Ruliad. Those are things like black holes or decidable expressions in metamathematics. Those are places where there is a unique canonical form. Basically, in a black hole, you can come at a black hole from all different angles, but you're still going to go splat at the same space-time singularity in the center. So in a sense, that's what a fixed point means in the case of navigating space-time. In the case of navigating a metamathematics, it's a little bit more subtle, but it's basically that you're getting channeled into this thing which is a decidable theory where you eventually can come up with a true-false answer and you can't get sort of stuck with this undecidable thing that's going forever. Let's see. So there's a question from Otis here. How is it non-local? If it updates each node one by one, aren't all of them next to each other? It is local on the tree, but it is not local. It's a piece of tree that is local, but it is not local if you write the expression out as a linear string. And so that's the sense of non-locality. And the problem is that you can have sections of the lambda that are you're sort of taking out a section of the lambda, you're feeding it into another part of the lambda, and that's so you're essentially taking a big chunk of tree and you're reattaching it another chunk of tree in a very non-local way. You're sort of transforming a piece of tree through a tree to put it into another part of the tree. And so that's the nasty non-locality that happens. In the case of combinators, I had this rather nice scheme with directed acyclic graphs that allows one to sort of maximally not have to do that kind of copy operation. I think there may be ways, and it's a very interesting challenge that a number of people have tried to take up over the years, of sort of maximally non-copying a beta reduction. In other words, you're doing beta reductions, you pick your updating order, pick other things, and you have a strategy, an evaluator that maximally doesn't have to copy things. If you remember those pictures of multiway graphs, I had of string diagrams, I had these places where there is a copy operation. And the question is, can you avoid that copy operation in the evaluation that you do of a lambda? And that's a thing that's very interesting to try to figure out. Is there a way of rewriting the lambda to sort of, or evaluating the lambda so as to avoid those copy operations? That's something of practical importance in doing functional programming and so on. All right. Well, I think that's it for the world of lambdas. So thanks for joining me for this Lambda Fest. I feel I have avoided lambdas for decades because I thought they were kind of complicated. They are kind of complicated, as we've seen, but now we've kind of, I think, cracked their Ruliology, and it's probably one of the last remaining kind of simple systems where I've just never touched its Ruliology, and now we have. And so we can go on and study other things. I have a whole collection of Ruliological projects that are underway right now that actually in some cases build on this project. There are all kinds of questions about adaptive evolution of lambdas, about computational complexity of lambdas, all sorts of fun things to come also in the case of other types of Ruliological systems. But for now, thanks for joining me for this Festival of Lambdas. And lambdas have been, they will hit their 100th anniversary in another few years. but this was a pre-centenary celebration of lambdas. Thanks for joining me. See you another time. Bye for now.